I want to be live from downtown Mill Bay. We are now live from downtown Mill Bay. Classroom. Someone said, how do we know what the quiz is on? I posted the quiz. Generative AI for educators. Please go away. Chemistry 12. So, I put in your quiz day. It's currently on the wrong day. But when I post it, I told you what KBATS it is. Oops. So KBAT A1 through A5. So if you go down to your, you have this as a handout, KBATS, you should be able to do A1 through A5. Give examples of reactions proceeding at different rates. Describe the rate in terms of some quantity per unit time. Experimentally determine the rate of reaction. That's actually a lab, but we did a little demo. And you have done a little lab. Identify properties that can be monitored in order to determine the reaction rate. Your Hebden for the entire year is here. And we're kind of up to here-ish. I don't always remember to move that. And so Evan appointed himself captain. He said he would. So far he hasn't. I've already moved it. But generally, if you look at it and you go like, yeah, this set looks familiar to class, you should be able to see. So if this hasn't moved, but you know we've moved on, then like, oh yes, oh gosh, that should probably move up. We're almost done A. We're going to start B, which is energy diagrams and reaction mechanisms. So that's where we should be-ish on your Hebden. And last one is if you're like, what did that KBAT mean from the first day? Quiz day, KBAT A1 through A5. In addition to your Hebden, you can also study. So you go in here, you grab, it doesn't matter what number, it just matters that you use the same number. So P is an actual exam with like questions. And then, which one did I grab? This is 004. So I'll go back to 004 and grab PK. That means it's the key. So tomorrow, I would expect you to be able to do questions 1 and 2 off of this test. The answers are B for the first one and A for the second one. And they cover KBATs, they call them PLOs, A1 and A3. Do they have any short answer? Oh yeah, here's not a short answer, here's a long answer question. Theoretically, you should be able to do that. So we go back to the exam, go back to question number 1. Which of the following reactions is the fastest?
D.
Pardon?
D.
Why?
Aqueous.
Aqueous. So we did that little line. These are the aqueous is faster than solids and liquids. Sorry, aqueous is faster than liquids and gases, which are faster than solids. So B is clearly the fastest. Checks that you know that. Checks that you're not disturbed by the fact that it gives off a solid, because that's not what's reacting, so who cares? And that you look at that. This is a solid and a gas, slow, solid. 2 gases, fast, but not as fast as aqueous. Aqueous and aqueous and aqueous. Now this one, D is a possibility. Why not D? There's a lot of hand, because I heard so many words. And when I said hand, you just nodded. Yes? Hold it. They're yelling. Go.
There's more bonds to break than that one.
More bonds to break.
The
Yeah.
other one doesn't want to break.
So there's so much more going on here. So many more pieces. That's just going to be a little bit slower than something that's just going boom. You should also be able to do this, the next one. Consider the graph for the following reaction. Where is the average rate of the reaction the greatest? 0 to 1 minute, 0 to 2, 0 to 3, 0 to 4. The average rate of reaction is the greatest in what time interval?
0
Pardon?
0 to 1.
Why?
Because it has the steepest slope.
The steepest slope, yeah. Whereas if you do 0 to 4, like you're just averaging all of it, and it's getting slower as time goes on. The rest of them you might be able to do, but we haven't covered it. And then Consider the following reaction. A 0.24 gram sample of magnesium reacts completely with HCl in 14 seconds. Calculate the average rate of consumption of HCl in moles per second. So similar to what you did on the board, and there's some practice ones in the Hebden. As well, the Hebden is a minimum. If you just want to go do them all and not skip any, that is a useful thing, especially if you're not understanding the material. If you understand the material and you just need more practice, do more of these. You can pick apart all the old exams. We don't cover, sorry, I haven't mentioned this before. In grade 8, they show you a periodic table, you do a couple things. Grade 9, you redo that and you show them the Bohr model usually. You do a bit of Bohr model in grade 8 too. Grade 10, you redo all of grade 9 and just do a little bit more with reactions. Then grade 11, you redid grade 10 in probably a month or two and then all new stuff. And then grade 12, we don't redo anything. I don't know why the BC curriculum likes that and then stops. So you should be able to know how to like go grams to moles and moles to grams. If it's been a while since you reviewed that, review it. If you need like an old Chem 11 Hebden, I can probably find you one to give you so you can do a little bit of practice and get up to speed. And then that way you can do that. So you would be able to calculate that. Where do I get my quiz questions from? All these old exams. I may change the question, may change the numbers, but if you do these questions, they're in the same style because they were written by professionals who wanted to test as opposed to teach in a particular context. So they are actually assessed and at certain levels, whether it's knowledge, understanding, critical analysis, lab, that sort of thing. Okay, that's enough exposition. You hate movies where it's just talking about the exposition rather than showing you. So we were all the way up here. Compare and contrast factors affecting the rates of both homogeneous and heterogeneous reactions. Reactions are in the same phase as homogeneous. Gas, aqueous, liquid. We've already answered why not solid, because that's separate, so it's actually heterogeneous. And somewhere here, I have my own notes so I don't get lost. Solid, liquid. Oh, yeah. You have solid, liquid. What are some other ones? Are you laughing at your calculator?
Yeah.
Put away the calculator. It's bad as a phone right now. What are you doing? Oh, you're trying to do the question. Stop that. Not like studying class. What's another example of a heterogeneous reaction? Solid, liquid.
Liquid gas.
Liquid gas. So gas, bubble. Gas, liquid.
Wait, yeah.
Liquid gas and gas liquid are the same thing.
Solid gas.
Hand was up.
Yeah, sorry, do you have an extra?
Oh, right. You asked me that. Yeah, I'll go get it right away. And then there's the last one that I think we said last day but didn't write it down. There is a situation in which liquid is heterogeneous. What situation is that?
Oil and water.
Not oil. That's
No,
what
no,
What?
oil and water.
Oil and water, yes. So if they're not what's called miscible, miscible means they can dissolve in each other. If they're immiscible, then they do not. I can get you science 10. There is one you can also print that's uploaded. I'm guessing you didn't see that. No, like we had one. Unless someone secretly came in here and threw them in recycling, which I'm starting to suspect. These are new. There's one. There's only a couple left. There you go. Sorry about that. No, last minute. So, things that are heterogeneous are affected by surface area, which is why we had to grind zinc up into little bits and get it to go faster, and then we can put it in, and then we got more hydrochloric acid. Liquid, as long as they are immiscible. No, if they're miscible, that means that they do join. So the miscible, they're homogeneous. If they're immiscible, they are heterogeneous.
Why not gas and gas?
Oh, gas
Yeah.
is homogeneous. Gases, there is no such thing as an immiscible gas, as far as I know. If someone can contradict that, pardon? Pardon? Liquids can be in the same phase. So to be heterogeneous, they have to be like oil and water. Oil and water. They have to be so that they literally separate. But if they don't separate, then they're homogeneous. So the demo was how finely ground is our solid zinc. You can burn a log, or what is it that you want to get when you're getting the fire going in Eco Challenge? You don't just light the log on fire. Pardon? Yeah, you're trying to boil water, but how do you get the fire going quickly? Paper. Paper is wood, but it has way more surface area, so it burns quickly and you can get the fire going faster. Paper has lots of surface area. Burning log has less surface area. We're still not allowed to actually go out to the lab yet. They're not quite commissioned. I do have a demo. We're allowed to do demos. I confirmed. I actually had to beg Miss Allen yesterday to be able to do that. But it will probably be next week. As I go on, every once in a while you'll see some page numbers come up. That's roughly the section of where we are in the Hebden for this particular topic. You don't have to write them down. They are on the live stream because it is on the, as we go along, it is on the Hebden list as well. But they're not the same. They're just like all of them. So like these questions cover that section. And then if you're getting it and you're just going to do the minimum, then you can just do the minimum. If you want to do all of them, I recommend doing more than the minimum for most things. A7, discuss situations in which the rates of reactions must be controlled. Read page 10. So this is an assigned reading. I want you to do that in prep. And it has things like, why are your laptops out? Put your laptops away from your bags. Laptops. Just gives you a few examples. Things like body chemistry, fuel burning, fires. It's just a list of examples. Ideally, you should be able to come up with your own examples. And I feel like we've already done that in class. So I just say it's a reading. Look at examples A to G. Make sure that you're familiar with some examples and you're good. Theoretically, we are now done the introduction to reaction rates. What's on this page? Right. Oh, there's it. So, reaction rates is questions 1 to 17 and page 1 to 10 in your Hebden. Now you should be able to attempt all of those. And we're going to start the next section. So this is just the introduction. The next section we're going to do is the energy diagrams. But before I do that, so it's 12:14, and we just finished it off. If you would like to take, let's say, give you 15 minutes to take your book out, do a couple of Hebden questions, ask me a question, go online and see where all that stuff is. We'll start up again at, say, 12:30, and I'm going to do the next one. So a little bit of work time in class. Yes. I don't have my spreadsheet and everything set up, and I want to be able to give it back right away. Please don't do what? Oh. You don't hang. You may pull out your laptops and look at questions. It would be really cool if I said, you can now look at the questions in the Google Classroom. That you had to like just imagine. Or use a text-based browser.
Page 8? Is it
No, a text-based web browser. A web browser that can't show pictures. It can only do text. Oh, cool.
Oh, that's
Wait, are we supposed to do 12?
Yeah. Yeah. I just
I don't know the questions. It just says I don't know the
You
questions.
can email it. I downloaded like last year the first, I can't remember what it was called, the first ever web browser, and it was text only because I thought it'd be useful because there's it gets rid of all the ads. You just get a little word. That's super useful. Yeah, you can still see them, but then it takes away any distraction. Oh, I like that.
I would hear you.
1, 2, 3, 4. 1, 2, 3, 4,
So when you not write your
6. 1, 2, 3, 4. Yeah,
Is there an online version?
I will make one right now. And I'll put it in the same folder. Did you find the folder for the first one?
I did, yes.
Okay.
I found the PDF.
Yeah. There's a link to the folder, and I'm going to just put them all in the same folder.
When's the first if it doesn't, it's not not this Thursday. Next Thursday.
3:16. Yes.
For this question, how would you want it to be? I also want the answers to show. Does it ask what is the rate? Are you really sure?
Well, the rate here is moles per second, so your rate of production could also be moles per second.
NH3.
Yep. Just let me export this file, simply because, so we can get it 3 to 16. Where's that? Adobe.
You know what's funny? It's playing. Well, do volleyball. Okay. Have you tried it? Yeah. It's not. No, yeah. Sometimes I will try to get those glasses. It's true. I like. Wearing glasses. Or like popping on the see when you play just messes with your depth. I did.
Okay, the PDF should be there now. Of course.
How do I compare which factors are important? As well as factors are like these ones, right?
Yes.
How
All of them.
how would I do that?
So let me take, where's the question? Because I might be making some 15. Which of the 6 factors are important in homogeneous? Oh, so in the question interpretation, they are asking you what are important in homogeneous. So you just look at it. But there's in heterogeneous, there is one that is important there that's not
recipe book.
all the ones that are important.
It's hilarious.
But in heterogeneous, there is an extra factor.
Oh yeah, and it just walks always.
How do we determine if it's like homogeneous
All.
reaction? It doesn't matter about.
All the ones that apply. So you said, you look back and you're like, for homogeneous temperatures.
Can I just do a
Yeah.
short answer?
Those were
Because I
all
feel like
important
it's
for,
Ability of reactants to meet.
right, and when is that important?
Because
Surface
I
area.
okay, when I
So that would be,
okay.
so.
And that, was that important for heterogeneous or homogeneous?
Oh, I,
Mhm.
Sorry for this one, can we not do advances, but we have to show that one as well. Because if you just subtract that from the advance.
2
The
hours.
following pairs of your, oh, so this is a pair.
I think the fact you subtract it and get the answer is an accident. Oh, no, you have to subtract. H2 is initially 2.7. After 2 hours, it's 1.3. So you go 2.7 minus 1.3, you get 1.4. But now we're calculating it in terms of HI. So this is 1.4 per 2 hours.
Yeah, but you don't have to show this. Because you're just doing something.
To 1.4. Well, from here to there, you wouldn't do that way because like it's initially 2.7, but not all of it reacting. Like it wouldn't go over like that.
Okay, so just show this one.
Just show this part of it, and you just have to show that you took. This is more like moles of H. Okay, wait on this. Okay, moles of H2 is moles H2 initial final minus moles of H2 initial. It's just 2.7 minus 1.3 equals 1.4 moles. It's not actually part of any table. This is just our value of H2. It was made in 2 hours. And the rate is 1.4 divided by 2 hours, if you want it per hour. But what you're doing correctly is this ratio is 2 to 1, so once you get that result, then you multiply by 2. And because that divided by 2 hours and then multiplied by 1 to 2 ratio comes out to 1.4 again. You,
So normally I shouldn't do this.
no. I just realized that question, you get 1.4 so many times.
You think
That's
sometimes
the best question.
Choose like the
I
other.
should change that.
Softens roll down, pull it up, right now.
like stands by like the backboard.
It's so scary.
And are we done?
Which are important in heterogeneous reactions? I wrote.
No, no.
All are important.
Why? I'm trying to do it.
You're not telling me the answer. You're just saying all but. I didn't tell you what the answer was. I don't know the answer.
Okay.
Chemistry 12. Beaches is here. How many people are there? 1, 2, 3, 4, 5.
On Friday, so there's a week on that day as well. So.
You're gone on Friday?
Yeah, that's.
We don't have parking.
But Saturday's the test. So you wanna do it on
You could do it Thursday tutorial.
Oh, that's, I don't think I could.
Are you quickly coming up with a reason?
No, I'm just not prepared.
Tuesday tutorial.
Okay.
Okay. Done. Deal.
Thank you.
What sport?
Oh,
What sport are you doing after volleyball?
maybe hockey?
So competitive sport after competitive sport?
Well, if I can, all 3 terms, yes.
Fair enough.
But you would still have to go to practices, which means that we would have to leave classes.
6, 7, 8, 9,
They're not-
10.
Yeah, I probably wouldn't leave for games.
Yeah,
Yeah.
you wouldn't be able to play.
Dude, I already got a scare this year. I'm like lucky quitting.
Do women's weight training.
No. It's so depressing in the second term.
Just become a rower.
I did that last year.
Are you a rower though? Still.
I'm in rowing, I'm not a rower.
I'm in rowing.
Yeah.
I
Are you
teach,
still a
but I'm not.
novice? Are you still a novice? Or?
No, I'm in senior women's. We just have 6 days. No, because I don't do the rowing meetings.
I think that just makes you more attitude.
Well,
She's
no,
just a
it's
little
because-
bit brain bomb.
it's because I have other sports, so I can't go to rowing.
You're trying to do everything.
And then yeah, do you want to give me like some, mentally, do you want to like, take that and then down like a try hard and then
Well,
Oh, no.
the discussion I have with all my advisees is you can do anything you want, but you can't do everything, because then you'll stop being good at the things you were doing.
you know that's true.
So don't half-ass things, whole-ass them.
Mm. Speaking of this question, I watched the live stream and you said for the people that aren't here, you don't get to see the work because you're not here. I don't know how to do it.
I think it's just because we moved on. Hold it.
Yeah, I was a little confused about that.
We did it on the board, and some things we do on the board.
No, you wrote the answer and you were like, you're not here, so you don't get to know how it's done.
But you can do that. You can
Well,
look
no,
at
I
it and
did
do it.
copy this stuff.
Yes, but how did you do that?
I didn't.
Yeah, you can.
Okay.
Let's say.
I think word copy is just kind of
No, you can see the mathematical. That's 2.10. Forget the times doesn't
Elena,
matter.
you just have to
2.10. Okay? And this is in a 2-1-3 ratio. What do you notice about this?
It's like one side is
This one is decreased by 2.5. 1.5.
Yeah.
This one's increased by 1.5.
Right.
Okay.
Yeah.
Yes.
you're talking about 9, 8, right?
Nope. We're letting this settle for a
That's
second.
the coefficient.
Well, this one's decreasing. This says
Yeah.
increase.
Now, it's decreasing by a ratio.
Oh, because you're just doing them.
Yeah. So all we did is we
Is
took.
divide by 2 and then switch over.
Yeah.
Oh, okay,
So
okay.
rates can move across like stoichiometry. The reason I deliberately hold back from telling you is if you figure that out yourself, you usually will remember it longer.
And you suggest the table method? Okay.
The table method, you can use it in class. I showed here. You can also just multiply by the ratio. So you multiply where you're going to divided by where you're coming from. So you can just like multiply. If you're going from there to there, you can say multiply. Take that number and just go multiply it by 1b divided by 2a, and then the actual chemicals cross out. It's just a quick way because you don't have to get out the whole table when you're not converting to like grams and everything else.
But you wouldn't like dog components?
No, absolutely not. No, we teach it that way because it's a nice way to organize it. Yeah. It's just sometimes it seems like a lot extra. Absolutely not. Yes.
Number 16 is
State 5 ways of increasing. Oh yeah, that's good. That's a really good one. What ways would you do it?
well, it's a closed system,
Mhm.
so does it mean like ways to change it without opening it?
It didn't say that. I don't know if the answer's going to say that, but I wouldn't assume that. So you have this reaction in a closed system. But if it was in an open system, what would happen? The gas would go away and it would stop reacting because all your reactants would be gone. Or at least those would. So how do you make it go faster?
Use ground up aluminum.
Ground up aluminum, so increase the surface area.
Oh, increase surface area.
Or grind it up is a way of saying.
I just don't know what.
Well, you can go through
It's
it.
like pressure.
Pressure. So is there a gas in there?
Yeah.
So increase the pressure there. So you can just go through those temperature, pressure, concentration. If there's a concentration, like you need a liquid for it, so you can see which ones are applicable.
You said not to use RXN.
Oh, what I mean, you can use the word, RXN just means reaction. But if you're like writing an essay or an answer, you actually have to write out the whole word. Reaction is just like in your notes, point form. And I use it because when I wrote notes in university, that's what I used. Oh, it's 12:31.
Mr. Nuva,
Yes.
how do I do the rise over run?
Yeah.
How do you, like in general, like how do you do a rise over run?
No, like in the question.
No, but I was just going to show you how to do a rise over run. That's not what you're asking.
Well, like I just don't understand
Well, you have
how
to,
I do it.
you have to graph it.
Yeah, I did.
And then, well, ahead about. So let's say,
But it's going down.
pardon?
The graph's going down.
Yeah, but rise over run doesn't matter if it's going down or not. You do the same calculation. You just get that, You have x over y. Oops. And you can go like that. So that's you'll measure that. So the rise is negative, and then you have a run, which is positive. Negative because you're going down.
Yeah.
So you're just making a triangle. So rise over run. And don't you learn like a, oh, sorry. It's been a while since I've graphed. I think your math classes all tell you that x is on the bottom and y is on the side. Right. So you go x2 minus x1 over y2 minus y1, and you use those points.
Wait. And then I divide. That's the rise. And then I would divide it by 30.
Yeah. So let's say,
But
let's,
it's not negative.
pardon?
This is negative, but it's not negative.
Well, you may have done it in a way that's not negative. Watch. Let's say you're going to make this your triangle, and so this is 1, and that is 2 for x1. Oh, sorry,
Why?
y. So that is y1 and y2, and then that's your starting point again. So this is x1, and that is x2. When I go x2 minus x1, I will get a positive number, right? Because going this way, this is bigger. When I'm going down, this is smaller, and I'm going to go y2 minus y1. That's going to be a negative number. And then rise over run, I'm going to have a negative number over a positive number. I'm going to get a negative number. What you may have done, if you look here, you may have just minus big from little, and you just got two positive numbers. You got the same answer, but you won't get the correct sign. So when you're picking your 1 and 2, it doesn't matter which way you do it, but you have to make a complete, like corner, and then you count, like that's 1, that's 2, that's 1 for the next one, that's 2, and you go around. If you do that, you'll always get the correct sign.
So I subtracted, and then about that,
Yeah. Another way to think of it,
and then I divided it by that.
yeah. Another way to think of it is with these two sides. Because I don't actually do this method. I just look at it and I go, oh, this, because it's going this way, I'm going down.
So it would be negative.
And it'll be negative, and I'm going across. So going across from left to right is always positive. Going down is always negative. So I just calculate it and then make it negative. So minus big for middle, minus big for little. If you have one like this, you are going across, which is positive, and up, which is positive. And if you, and then those are basically the only two you can have, other than straight up or straight across. But that would be weird.
I was like, this makes sense, kind of. Is this part kind of?
No, I was like, oh, I like didn't.
So these types of graphs are always positive. Ah. And these types of graphs are always negative. But I do remember being very pedantic when I used to do that, so that I would always have the sign pop out in my calculations. And that can help train it too. Does that make sense?
Yeah.
Okay. It is 12:36. If you can put away what you have, get out your reaction kinetics work. We're going to talk about collisions.
Oh, on Thursday.
We're making a podcast right now.
On what?
It's there's this podcast with this and that, and it's basically like they make like stuff up, so they take like an issue. And
Okay, laptops away. Bring up the notes. What were you doing, Evan? Because you looked like you were having more fun with that laptop. I did sneak up behind a grade 12 student. They were like doing library blocks, and they were giggling and laughing and clearly watching a movie. And I was like, they're not doing what they're supposed to be doing. And I came up, and then they turned around. They're like, this is so great. They're watching a video on Indigenous history, and they're in a really fascinating section of it. And they just thought it was really cool. They were just, well, not laughing at it. They were just like enjoying, learning. And then I had actually mistook the experience of joy for learning as just being bad. Because nobody should have fun learning. Never.
What is nerd?
Totally. Demonstrating awareness. You're all in chemistry 12. You can't really say that. Demonstrate awareness of the following. What are reactions? Like, how do reactions happen? Yeah. What's that called? Collisions. They're a result of collisions. I think I mentioned in my, the reaction, the collision theory of dating. If you want more chances, you have to go and collide with more people. That's not literally, but walking around and asking everybody out, somebody will lower their standards. Same with reactions. If you have more collisions, more chances of finding a successful collision. Only some collisions are successful. So if you go around, ask a bunch of people out, and you're like, well, I asked 5 people and they all said they don't like me, so I will never ask anybody again. Yeah, that's normal. Most people don't like you. Or at least that's the advice that was given to me. Maybe they were just saying something about me. Some of those will create a product. At this point, my analogy breaks down because now I have to talk about babies, and this is not biology 12, so we'll just leave that there. However, it does work for this. To have a successful collision, you need 2 things. What 2 things do you need? You need enough energy, right? In the dating example, you need enough money. You need enough money to go out, you need to dress up in nice clothes, put yourself together. The other thing you need. Oh, you need to actually find someone. Yes, but we're assuming there's a collision. How are we going to have a successful one? That can help collide faster because you're very attracted to each other. Gaze across the room, positive and negative. By the way, that's only true in chemistry. In real life, opposites tend to not attract. But time to get to know. My analogy is now causing, I think, more problems. You need the correct geometry. So if you're in the wrong position, you're not going to get a successful collision. You go on a date and the one person is like on their phone the whole time and never looks at the other person. You're both, sitting in a restaurant, you're facing the opposite way. You have to at least talk to them. You need enough energy, but then you need sufficient geometry. So, correct geometry and sufficient energy. So you need to have enough of both. If you're colliding in the wrong way over and over and over again, it's never going to work. If you have sufficient energy, great. If you can collide in the correct geometry all you want, but if there's not enough energy there, it's like, no. You need to bring a little more to the table. Now, one way to increase the speed or increase the reaction rate is we can just increase the number of collisions. What are some ways that we increase the number of collisions? Heat, just make them go faster, they'll collide more often. Also increase the amount of energy that way, so we get 2 for 1. How else could you increase the number of collisions? Heat and surface area. If they're all bound up and they can't collide. So most of those methods that we learned last, increasing the pressure, increasing the concentration, they're all just providing ways to increase the frequency of collisions. Now, we're going to do a bit of focus on energy changes. I've just showed Ms. Carroll. I've got a demo that I've got permission to use. We'll probably see it next week. We can actually see the mid-product where the bonds are fully broken and not yet formed. It's a fairly unusual thing to be able to see, and I've got one demo for it. And she is going to borrow it for her class. But all of chemistry is about breaking a bond and then reforming it in a new way. So we have to hit with enough energy to break the old bonds and then have the correct geometry so the new ones that are formed, you get the correct product. What do we call energy of motion? It's kinetic energy. So everything starts off with kinetic energy, energy of motion. And what is potential energy? What does an object must possess in order to have that? It hasn't turned, but how do you know something has a lot of kinetic energy? Here, I'll do a demo. Let's take something like really heavy. So, and then, I feel like I know how well enough to do that. We can all feel the danger when I go like this. So, what do I have to do to get this more potential energy?
Put it higher.
Put it higher. And then you give it kinetic energy? Let go. So, that is energy of position. Even in chemical bonding, it's energy of position. As the electrons go into different places in their energy levels. So it's all position. It's just how we interpret position sometimes changes. So that one, this doesn't look like it came over quite right. That's supposed to be potential energy. And when we're talking about position in terms of molecules, we're often talking about attraction and repulsion. So electrons repel each other because they're all negative, but they're really attracted to the nuclei because they're positive. And that sum of all those forces, where that atom is or where that electron is, will have a whole sum of forces that will lead to it either having a lot of potential energy or very little potential energy. But hold it. Didn't ask the question. Anybody not done? Good. Okay. It's the waterfall analogy. So we are Let's see my drawing abilities. Excellent. Now let's make sure it's all grouped right. Mr. Norman, Olympic kayaker. Don't ungroup. Lock. Let's keep Mr. on. I'll move and rotate. Yeah, okay. Okay, Mr. Norman. Up here, what does it have a lot of? Potential energy. Now I'm using Mr. Norman because I know Mr. Norman's going to come out of there alive. Comes down. Now what does he have a lot of? Kinetic energy. Goes shooting across because he picked up all that speed. What I would like you to do with this silly analogy, I would like you to graph on that table the potential and kinetic energy with two different colored pens, or dots and dashes if you don't have two colored pens. And we'll leave Mr. Norman there on the precipice. I once saw him in the middle of a river when a student said, I think I might be in trouble. He was over there in 2 seconds. He picked up their entire kayak in one hand and just threw it to a part of the river that he thought was better for them. The man's a beast.
You mean like, what kind of graphs?
Pardon?
What kind of graphs?
Like potential.
Potential and kinetic energy.
What?
They're relative to each other. So,
Line graph?
so you should put whatever's like, oh yeah, line graph. Were you going to do a bar graph? Okay, okay, okay.
On the bottom,
Good
right?
work.
This is, now often we put this as time, but I'm not going to put it as time. This is as river length. So this would be 0, and that would be 100, but we're not going to put numbers on it. If we were a chemical reaction, now that roughly corresponds to time, and some students will like, oh, it's time because over time he's going there. You get roughly the same graph. But in a chemistry reaction, we would actually call it a reaction coordinate. And all that means is as the reaction occurs, what happens to the energy. So it's just assuming the reaction occurs. This is assuming he goes down the river. I mean, he could decide halfway down the waterfall and decide to go back and just paddle up the waterfall and go back the other way. It's Mr. Norman, he could do that. But we're going to assume what happens to the energy. And then I'm about to ask you which one's high, which one's low, and what does it look like?
Would the potential energy like be high to start, or would it shoot up right before he went down?
Ooh, what do you think?
I think it would go up before he went
Why?
down. Because he doesn't have the like potential energy back there because there's not like.
Oh, I see what you mean. Why doesn't with respect to down here, does he have the potential energy down there? If I say with respect, don't do that. With respect to this point right here, when he's here, does he have potential energy?
Yes.
Yeah. Does it matter where he is up there?
I guess not.
No. If you probably
But
don't.
even if he was like all the way back there.
Yeah, even back then, it's still with respect to that point, he has potential
But
energy.
it would get more and more as.
Would the amount of energy he have increase as he gets closer to it?
Well, it would because technically the one would become faster.
Would it?
Yeah,
Why?
because like it's going down. It's like
The water will increase while it's going
no,
down.
like right before.
Have you been in the precipice of a waterfall before?
No,
Ah, the water doesn't speed up.
it did.
No, because it just goes. Shh. If you were in a car,
But it's being like sucked.
yeah, but if you're in a car, just forget all that. You're in a car and you're driving 50 kilometers an hour, and you approach a cliff, and like, I don't know, you have magic parachutes, you're not going to die because this would be a sad story otherwise. You're approaching a cliff, and then you go over the cliff. At what point do you start to speed up? Yeah, once gravity takes a hold of you and you start going down. But is there something that pulls you towards the cliff that increases the energy in any way? No. Same with the water. The water will not speed up until it drops. So his potential energy doesn't increase. For his potential energy to increase, he would have to go up first. If I dug a hole on campus, like a deep hole filled with lime on the bottom to get rid of all the, the bad pretty boys, you still have potential energy if I was going to throw people in that hole, no matter where you are on campus, because you would still fall in the hole. What you're, I think, confusing is the opportunity to do it. He doesn't have much of an opportunity here because he's not near it, but he still has that energy in comparison to it. Yeah.
With the kinetic energy, it will increases once he goes.
Yeah, there you go. I think mostly you've just answered everything. So now I'm going to just move to the rest of the class now. Let me ask Isabel, where does potential energy start?
Here,
Here?
yeah, and it increases. Wait,
Potential energy?
no, kinetic energy.
Kinetic, and excellent. So we got kinetic energy starting on the bottom. Where does potential energy start? Top. So I'm going to do potential energy in blue because I like blue. And I like pink, so we'll use that for the bottom. And then he's moving along. Just like that. What happens to the graph there? No. For this portion. Stays even. So you should have a straight section. So there's his kinetic energy is whatever it is. It's low. And then, pure Mr. Norman style, what's happening? A lot of kinetic energy. What's happening to the potential? Yeah, so it's getting converted. And then he hits the bottom. So they should what? So kinetic goes up. Sure. And then potential goes down.
Would it slope like that, or would it just drop straight?
Yeah, wouldn't it just drop straight?
No, it's drop.
But once
Hold it.
gravity.
But you're not dropping to get a.
No, but when you have height, you still have potential energy.
Right. I think what I have is too much of a curve here.
And it takes like, you just immediately get up to your like, max speed.
Yeah, because his mass isn't changing if we switch over to physics. And when you start and gravity takes a hold of you, you're going to start to accelerate. But as you go faster and faster, you will get more and more energy. So yeah, your kinetic energy is going to start slow and then get a curve up to here until he hits the bottom, at which point it's an abrupt stop. Or if he manages to like slow himself in some way with his paddles. I don't know. He's a genius. And then the potential energy will start off in the same way. Oh, I know how to do this. Haha. Because how should these two graphs look compared to each other? Mirrors. So draw two mirror graphs. And I'm going to cheat. Oh, dear. Oh, no, that'll work. Flip. Nice. And then what should the graph look like as he goes along this way? Should it up, down, steady?
Potential energy go further down than that?
Shouldn't it drop fully?
It depends what our scale is.
But didn't you say the potential energy is high, like even when he's like all the way back there, so
Yep.
it would also go back to being high?
No, is he all the way at the top?
Well, there could be another drop, you know what I mean?
Well, there could be another drop. But we just picked there. He could drop again. That's absolutely true. There's no scale with this. So like, this could be 8.9 kilometers in the air for all I know. And so it's measured in joules, actually. But, I mean, he could drop again. So he could go along, and then like, oh my God, it's Cliff City, and he could have, and then what would happen to the potential energy? go further up. Shoo. So that is our second waterfall.
Although once he slows down, wouldn't the kinetic energy go back down?
Well, now you're thinking friction, right?
Sorry?
You're thinking friction now because of all the waste energy.
Well, sort of, like, because when he's at the top of that first waterfall,
Yeah, he's moving at steady speed.
low
Yeah,
kinetic energy,
yeah,
and then after, like, say this middle section
Yeah.
between that and the next
Yeah.
waterfall was
Yeah.
long,
yeah,
he would have the energy after landing the first
yeah,
sweet jump or
yeah.
whatever, and then he would eventually run out of the speed
No,
that he gained
no,
from that.
no, he never would. Never.
So
No,
there's
no,
zero friction.
no friction.
Scenario.
Just go, because then our graphs get complicated, and then I have to do like physics 12. It's chemistry 12.
Okay.
Stupid friction. Yes.
I don't understand why the potential energy wouldn't drop when he is like, if like there is no more drop, like there's not another drop, wouldn't the potential energy just like go all the way to the bottom? Because there's nothing else to drop off of.
It depends on your frame of reference. Right now, we would say we have zero potential energy. And then some mad person comes in here and digs a hole next to you and goes, ha-ha, now you do. You have potential energy as long as you're not at the center of the Earth. And even there, if you think you don't have potential energy, you're not at the center of the galaxy. There's always the potential for you to drop somewhere.
Okay.
Does that make sense?
Yeah.
Because you always could drop. No matter where you are, someone could dig a hole.
Okay.
Yeah. There's always the possibility of going down. Okay, reactions are the result of molecules colliding into one another. Many collisions produce no results. If there is enough energy, some collisions will cause a reaction to occur to form products. Oh, sorry. I probably moved that on too quick. The graph below, I would like you to draw. Actually, I want to see what you would draw. Because I think it's changed. It also gives you a little chance to get up and walk around. So and give you a chance to talk to someone new. Find a partner. If you don't have a partner, you can always join a different group. You can join any group you want. Find a spot on the board, race to it there, and draw that graph how you think you should draw. I want to see what your previous teacher taught you. What? You have a point? Oh, you have a point, yes. Lots of people have points, don't they?
No.
What? I haven't been using it very much. Oh, someone just got one. Because I didn't press enter before. Currently, Portia, Marcus, and Isabel all have a point. Yeah.
All of what?
A point. Like a point. Yeah.
Okay, we gotta draw this.
Draw that. Mm. And then once you've drawn it and you've labeled it, go sit down.
Or sorry, yeah, CL plus CL.
If you were completely out of space, I do have whiteboards at the back. Oh, good. Your teacher taught you lots of things. I like how people look over their shoulders. Yeah. Oh, I'm not telling you. Once you're done, you think you got it, have a seat. Are you second guessing yourself? Okay. Draw what you think is right. You can only see. I just want to see what different people draw.
Because everyone's doing the hump.
Did you do the hump last year?
See, me and Elena were in a lot of athletic,
Draw what you think is right. I just wanted to see what everybody would draw. We've got lots of interesting things. We have things that I was expecting. And some of you are cheaters and changed their minds. That's fine too. Some of you were not cheaters and you realized that you were wrong all along. It was Agatha all along. A lot of grade 11 classes do teach that. So if you have that, that's many grade 11 classes. However, if you're an AP or you had a teacher that just wanted to get in other things, you would have put reaction coordinates here. And, as many people did, you would have drawn the hump, as many of you seem to refer it as. Sounds a little weird, to be honest. I'll just put a dotted line here. Those of you who did it this way, what's that?
The
Activation energy.
Is that right? The hump?
Yeah, it is. So the only thing I want to say is the red, old, and it's just missing the activation energy. And to be honest, you didn't have to do it in Chem 11, and your textbook, if you did Hebden, doesn't have it in it. Sometimes I even introduce that in grade 10 sometimes, depending on what we're doing. But now in grade 12, we're going to introduce it this. This is the energy barrier. So when I say a reaction needs the correct amount of energy, and it needs the correct geometry, the energy part is in here. Because everything in this room could be reacting right now. What chemical reaction could apply to almost everything in this room? Pardon? Oxygen is involved. Oxidation. We could all be on fire. And that reaction would continue going spontaneously until everything was burned. But we're not currently on fire. Why?
Because
We're
there's
not
no
flammable.
reaction.
We are flammable. Oh yeah. Everything.
There's no
There's
reactor.
no activation.
There's no activation energy. This room's not hot enough to spontaneously activate on fire. I'd have to literally like walk around with a match and provide that activation energy to enough places. No, yeah.
Like if you held like a lighter to your skin, you would light on fire?
Well, no, you do contain a lot of water.
Die in fires.
But if you get
They
Well, they're-
burn.
Like, yeah, but they're like clothes or something burn.
Um,
They die of the heat.
Yeah, but do you think?
well,
like,
no,
there's
we don't need. Why are you arguing? Stop it.
I think your skin
Nope,
burns.
stop. You asked a question. To answer your question, are humans flammable? Yes and no. If you are, say, me, yeah. And this, have you heard of spontaneous human combustion?
Yeah.
That's been long solved. We know how it happens. It usually involves alcohol or some sort of barbiturate or drug in which the person remains unconscious because they don't wake up with what's about to happen. And then it involves a flame source, fireplace, lantern, something, and a low oxygenated room, which means the door's closed so fresh air can't come in. If something catches on fire, like the big sofa you're sitting in, and starts burning, it can burn you and it will ignite your fat. And then your fat will burn outside in a very concentrated way under low oxygen, so it just leaves ash behind. So that's why in old spontaneous combustion, like spontaneous combustion, they'll show like a whole leg that's been burned, but the rest of the body's fine. It's because it was burning the fat. They've managed to duplicate it, not in humans, but with pigs. Because they have similar, well, not similar, they actually had to feed the pigs to get them as fat as humans, because humans are actually fatter than pigs. Yeah, that's, yes. Humans are on average not as lean as pigs.
How?
have you
Pigs are massive.
fast food and candy? Like, it just is. Yeah. Now, if you are a very lean person, not much fat on you, it's actually harder for that process to happen because there's not as much to ignite. So yeah, it is possible. Okay, completely aside. Yeah. So if you were ever worried that you're going to walk down the street and spontaneously catch on fire because of spontaneous human combustion, no, that doesn't really happen. Okay. You literally have to be knocked unconscious. Okay. To briefly describe the activated complex, I'm going to label these, which is why I've drawn them for you. You have a reaction in which you have iodine that hits hydrogen gas really hard. And when it does so, they break their bonds and form hydrogen iodide. Pedantically, all the way from grade 9, what are these called? What's the left side of the reaction called? Starts with an R. Reactants. And pedantically, all the things on the right-hand side of the reaction are called? Products. How many of you are in biology? Those are called substrates in an enzyme reaction. The reason they call them substrates and not necessarily reactants is because they actually, depending on the enzyme cascade, become different things. And fitting into an enzyme has a substrate reaction where you have to fit, and so they use more complex terminology because more complex reaction. One of the things you have to add in here, let's go with a dotted line, and let's make it blue and dotted, is that the bonds here aren't quite broken, so you have the old bonds, and you have the new bonds. So, old attractions weakening. Let's call that A, so I don't have to rewrite the explanation over here. Those are the old attractions. This is a bit like when you graduate. All these people, they're dating in high school, they graduate, they have a bond, they go to different universities, the bond starts to break. They meet new people, new bonds form. New attraction forming. Not always the case, as Allard House shows. Julia, a student who I will not name, was dating a student in Privet House from like grade 10. And they continued all the way through high school, all the way through university, and now they have like 2, 3 children. Aww. Okay, so in our little graph, if I was to do this, these are our reactants, these are our products, but all of this is right there. It is the top of this little curve. It has the most energy because it has the most bonds. Most bonds, most energy. And that's why it takes, that's a really bad writing of energy. I'm just going to let you interpret that. And we call this thing, anybody here in AP, like Chem 11 AP? Did they do this?
Probably at some point.
Okay, I won't ask that. This is known as the activated complex.
Actually, I don't think so. I don't remember that word at all.
Okay. Well, they usually do at least do redox.
We did redox.
We did redox. We don't do redox till the end,
Leo Greer.
but you'll have it. Yeah, Leo Ger. So this is called the activated complex. It is an in-between molecule that has all of the bonds. It is midway. And it is high energy. And unstable. What kind of energy is it high in? It is activation energy, but is it potential or is it kinetic? Potential. Because all of the graphs we're going to draw, most of them are potential energy graphs. So it is a high potential energy.
Is it unstable just because of the way it's placed, or is it, are you talking about the molecules?
Pardon?
Why is it unstable? Is that just because where it is in the graph?
Oh, it's just because where it is in the graph. It has all of these bonds.
And it doesn't matter what the atoms are.
It doesn't matter. In any reaction, they will be completely bonded. And there's it's midway, but it hasn't broken the old bonds, and it hasn't completely formed the new bonds. And so it has all the bonds. But it has to fall down on either side. It's either not quite enough energy, and it's going to break the new bonds and become the old stuff again, or the old bonds will break, and you'll get the new stuff.
Is there any way to keep it in that state or no?
It's incredibly unstable. It's a bit, you can think of it a bit like, that's a peak. So if you rolled the ball to the top of a hill. Now on Earth, hills are often flat on top, but imagine a sharp peak. It's sitting there, it's got to go either way.
So you can't keep it.
You can't keep it there. Like I said, I have a demo where you can see it and it exists for whole seconds. It's incredibly unusual to find a reaction where you can see that process. Yeah. If I was in a lab and we were researching this, you'd throw it in an NMR machine, which is like MRI for molecules, and you just have second by second measurements of it, and you can capture what's going on. Okay. This is just to show, because that is all about the energy. This is to show, or just a reminder, you have the unstable activated complex. If it hits with enough energy, you break apart. But this has correct geometry. If they hit in the wrong way, boom, then you're not going to get it. It doesn't matter how much energy you have. You show up and nothing is right. Geometry completely wrong. Who cares how much money you have? I'm not dating you. You need to have the correct presentation as well. Bad presentation, no reaction. Define activation energy. Those of you who did it, since everybody defined it, how do you define the activation energy? The reaction energy required to start a reaction. So we have an example reaction here. I'll make this a little smaller. And we're going to start off. We're going to label this as a graph. Let's start off here. And we're going to end up, let's make it, if you start high with lots of potential, you end up low. What kind of reaction is that? Exothermic. So let's start high and end up low. I'm going to use that reaction as my example, A2 plus B2. And this is down here is going to be 2AB. Free energy is a form of potential energy. And then what would be the formula of the activated complex? Is that a bad bell? What do you get if you mush these together and it has all the bonds? A plus B. Well, you're separating the blood. Just all the bonds. A2, B2. That was the bell. So after that, you can go. Quiz on when? Do we have class? We have class tomorrow, though, right? Okay.
First blow. My baby she is.
We're probably doing it in 2 floors.
For men?
Sequencing setups.
Oop. Stop recording.